You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Today's podcast is sponsored by Synopsys. Our technology, your innovation. Our guest today is Hezi Zar. Hezi is an executive director of product line management for mobile, automotive, and consumer IP for the Synopsys Solutions Group. He brings more than 20 years of experience in the semiconductor and embedded systems industries and holds a BS in computer science and economics from Tel Aviv University and an MBA from Columbia Southern University. Hezi, thank you so much for joining us today.
Thank you for having me.
So we're going to talk today about chips at the edge, innovation for AI at the edge and in the automotive industry specifically. Let's set the stage a little bit. Edge AI is, of course, very rapidly evolving with advancements in model efficiency and hardware capabilities. Could you start by sharing your views on how these trends are shaping design requirements for edge devices, particularly around the all-important factors of power, performance, and cost?
Sure. Yeah, let me start by saying the revolution of AI is really impacting the semiconductor overall.
Yeah.
We are expecting AI chips to be in about more than $1 trillion by 2030.
Yeah.
But that's the majority of it is really right now being generated based on AI chips that are going to the cloud. That's a high performance compute that is been driving the innovation around us. But in order for AI to be successful, we as consumers need to be using it. And so when we're talking about AI at the edge or AI on device, talking about AI that is accessible for us as consumers. So starting with phones and laptops and computing, but going into automotive, AR, VR, and other kind of autonomous electronics such as robotics. This is really what we're seeing at the moment as the innovation cycle that we're experiencing. So we are seeing heavier investments in R&D going into adding AI for the consumer or the edge that is typically providing better ROI, better economics for semiconductors going after this. The reason for having the consumer use more AI at the edge is there's a lot of advantages. The first and foremost is the economics of it. A less reliance on the cloud means that it's probably cheaper for us and actually can be used by more and more applications if AI can be operational mostly on the edge or sometime in hybrid model. So less usage of the cloud, quick response for what we want, more personalization. The device itself can know more about us, increasing security, increasing privacy, all of that is really happening. Now, the thing is with the challenge on the design is that AI, on-device AI is rapidly changing. And the models that have a quality index which is high are actually superseded with newer models that require less resources and still same quality. So we see innovation at the edge on the AI model. So models can become smarter and smaller and becoming more economical to use them on the device itself. The workloads themselves are moving out of the cloud. So in order for them to be useful at the edge and get all the on-device benefits, which we discussed, like privacy, security, and responsiveness, personalization, all of that, we see more and more capability at the edge. So smaller models, more capable models to be useful. However, it's at the end of the day, it's depending on the use case. And designers need to take into consideration flexibility, power, latency, performance, cost. All of that is really tied into the workload characteristics that are being used. So how much memory, how much compute, what is the I/O functionality that needs to be used. And the most important thing with AI on devices is really the bottleneck between the memory and the CPU. And memory is really where you store the model, and it could be mixed of experts. So you can have it on your storage device, such as UFS, eMMC, PCIe, etc. And the LPDDR, the memory itself, the cache memory to do all the computing. And so the bottleneck is the loading the information to the right place, making the compute happen. And this is really where the most of the challenges are going into this industry to get the latest speeds, latest capabilities. But really, when you're at the edge, you're bounded by space, you're bounded by power, et cetera, et cetera.
Yeah, so many restrictions when we start talking about things running on the user's device, and so many factors, and the pace of development, as you alluded to, is just mind-boggling right now. So you started talking a bit about the challenges inherent in this sort of architecture. Can we dive a little deeper into the challenges and what opportunities come with those challenges for designers, with Edge AI appearing in such a crazy wide range of devices, anything from smartphones to cars to industrial sensors or other applications? What are the biggest challenges that you see designers facing in trying to achieve that balance of scalability, security, and real-time performance? And if you can, talk to us a little bit about how design teams that you work with or interact with are managing the growing complexity of the standards and the various interfaces.
Yeah, I think I touched a little bit, but I think the biggest challenge that I see for hardware designers and designing silicon is that it takes time to get silicon out. There are newer nodes, there are newer requirements. The design cycle itself, it doesn't become shorter. So we need to do more work in shorter time. The challenge that is being added with AI is the fast progression of AI in general. So today requirements will not be tomorrow's requirements. So they need to work in a place where it's undefined exactly how we gonna how we going to service the market going forward. So you need to have a component of flexibility in your system. So the design itself need to be software first design. They have to look not from bottoms up. What do I do with the chip? How would the chip operate? It's actually the other way around. What is the workload that I need to be targeting? What profiles? Try to predict, albeit that this is the tough one.
Yeah.
But try to predict how it's going to service that. And then after you do the simulation, the software, then you do a hardware code design. So all of that needs to be done shift left. Getting the design done earlier on paper, let's call it this way, will enable us as an industry to utilize our resources in a better way. So stuff like where we're going to put your NPU. Is it everywhere in a system, or is it just your SoC? So it needs to be looking into the system level. Would you use training on device? Would you use heterogeneous compute? All of this needs to be taken into account. You ask about standards. And I touched about that on the previous question. So the bottleneck is definitely the compute power, so the NPUs, but getting the data, getting the model or models, getting enough storage and good latency that you can accommodate the use case, and then also a memory for do the computing. So specifically on that, I want to touch on JEDEC, UFS, and JEDEC LPDDR without exposing JEDEC roadmap or anything like that. But we're definitely seeing a demand for a faster JEDEC UFS. It's a universal flash storage that JEDEC is driving based on MIPI Unipro and MIPI MFI. And LPDDR, and specifically LPDDR6. So utilizing 7 billion plus model size LLM, you need 7 gigabytes of memory for 40 tops, then the memory bandwidth will need 70 gigabytes per second. So the traffic that needs to come in and out of the SoC in order to process the data is very important. So this is really what we need to pay attention to mostly, but there are other advancements in standardization. They're not as rapid as LPDDR and UFS, but they're something that designers need to pay attention to as well.
So speaking of rapid adoption, multi-die architecture is something that we've been talking on this program a lot lately. We're seeing a very rapid adoption of multi-die in HPC and in AI applications. What do you see as the trend in edge AI in terms of that, especially in the automotive sector? And I'd love for you to talk us through what advantages you see that multi-die is bringing to automotive applications, and how are these advantages different than for HPC or traditional data center AI?
Yeah, that's a great question. So, yeah, we're typically using or talking about multi-die in the industry in the context of high performance compute.
Yeah.
So, at the edge, there are also other systems that are doing higher performance than the typical edge, as we call it, edge. And these are computing engines as well as automotive. These are the first movers in the edge applications that are either considering or already using multi-die. So they, of course, first of all, they have a lot of compute. So they are the first ones to go in. I believe other applications will follow through. Their requirements for computing is not as critical as automotive and computing. But automotive is a good test case. So automotive is really a physical AI device at the edge, has all the sensing capability to make decisions. So the automotive SoC, typically, if you're looking at ADAS, has an AI-based level 2, level 3, or beyond ADAS for self-driving. They're adding generative AI digital assistant as well for the driver to be used for. So a lot of AI capabilities are in the car itself. And we are seeing actually good adoption of multi-die in automotive. The challenge with automotive is that partitioning the workloads into dies and chiplets is one thing, because you have multiple ways of scaling the functions across multiple dies. Then optimizing the multi-die for power and performance, and then check the architecture, how best to utilize that. In automotive in general, we are seeing a trend where semiconductor suppliers are looking into delivering family of products. So, for example, providing an SoC for the base model, for basic model for cars, and then for medium range, and then for high end. So the ability to provide different chips for that allows you to have flexibility and scalability to service the market needs in fast way that this market is moving. So what's different between high performance compute and the motivation in doing multi-die is that in high performance compute, typically the motivations are driven by aggregation and disaggregation. So the challenging is the die size and the yield, and the higher performance that you always need to have. While in automotive is mostly time to market and scalability. While of course you want to use the performance, but it's not necessarily the yield or the die size. That's not the limitation, but ability to service the multiple flavors of SoCs that you want to do. And for doing it, you don't need to do another automotive chip. It's expensive. It takes a long time for qualification. I'm not saying that multi-die is not. I'm just saying it's an ability for the industry, not a single vendor, the industry, to create ecosystem that will be able to service the multi-die use case in a controllable way.
So let's dive in a little deeper into the multi-die design process and talk a little bit about die-to-die connectivity. So UCIe has emerged as the de facto die-to-die standard. Is that enabling better die integration in automotive multi-die designs? And talk to us a little bit about what other considerations we need to be thinking about when we're considering multi-die design, particularly in automotive, where our tolerance for errors is obviously extremely low.
Yeah. So UCIe definitely drives the ecosystem, again, coming from the high performance compute. It's not just a technical standard. In our view, UCIe is really a strategic enabler for high performance compute, and now in automotive as well. So when you need a high performance compute or high performance die-to-die connectivity, UCIe is definitely has established itself as the standard. And UCIe has some consideration for automotive. It wasn't just created for high performance compute, but also auto. So there's a dedicated reliability reporting functionality being added to UCIe 1.0, 1.1. There were enhancements that were done in UCIe 2.0 and 3.0 to boost power efficiency, enhance manageability, fairly expansion on the design flexibility for scalability architectures. This is really crucial for the automotive market to ensure that all these functionalities are done in a way that is in a reliability model where automotive SoCs are needed. And the thing with UCIe, it provides a couple of use cases in automotive. One is the heterogeneous computing, where you have, in addition to the base die, you have an accelerator die. So having a low latency interoperable solution between the two dies is one. The other one is AI scaling, which is more homogeneous kind of use case, where you have two identical dies connected together to have knock-to-knock, low latency and coherency. And the last one, which I believe is going to be very popular in automotive industry, is that offloading the additional features outside of the base die. So you have the base die where it would have the majority of the functionality, but then you can compose a multi-die system by selecting the chiplets that you want. Now, we're not talking about here open chiplet market or anything like that, but more of a controlled environment. This is, we're still talking about automotive. So the ecosystem will have to ensure that the chiplet that has, let's say, infotainment expansion or I/O expansion or sensor fusion expansion or a lot of AI acceleration, then all of these are done in a controlled way that it's not a consumer market. It has to be done in a way that operation is guaranteed, like you have a single SoC. And we are seeing the industry moving to different initiatives to enable this kind of ecosystem. Well, just one example is Astra is a Japanese consortium that is able to, or targeting to do that, but there are other multi-die initiatives that we are part of it. But in general, we need to enable an ecosystem that will be able to service all of that. And you ask about challenges, I think it's important to mention it's not just UCIe, because you need to have some kind of monitors for silicon life management. This is very important because now when automotive market, which is known for its reliability, for concerns about safety, this is a new avenue for the industry to go for. So having sensors that are actually on die, so PVT sensors, for example, or other signal activity sensors there, will enable to have an improved lifetime operational metrics. We'll have to have predictive maintenance and reliability. So maintaining the circuits within spec, providing alerts for something happens. So this will not only, I guess, improve the operational side of things and avoid recalls, but actually provide the reliability information that is needed. And if something fails or something is about to fail or something that is outside of spec, there'll be an alert somewhere in the system that will enable the OEM to raise a flag and provide that to the driver, to the consumer itself, to go fix it, go do a maintenance. So I have to stop on the side because something is really potentially fatal.
Yeah, we've got dire consequences in the event of issues. Hezi, from the very beginning of our conversation, I could very distinctly hear your educational background coming through in your perspectives, that combination of computer science and economics and business. So I'm particularly excited to ask you my final question here, and that's about looking into the future. So as the edge AI models and hardware continue to advance at this crazy pace, what are you seeing as the next big opportunities or big challenges to overcome for IP design in real-time edge AI systems over the next few years? And are there emerging technologies or standards that you're particularly excited about?
Yeah, I would think that, first of all, the designer job is one side is easier, have more AI tools. On the other hand, market pressures that are happening and complexity that are
Faster,
happening.
cheaper, better.
Exactly. Shift left is definitely something that all designers are looking and will continue to look at, meaning do more in software, do more as design verification before you actually tape out. So having all the emulation, FPGA prototyping before you get silicon is critical. So what if exploration definitely will be done? And of course, in the semiconductor space, companies such as Synopsys will need to take ownership of the shift left, but as well as to enable high quality tape out and silicon bring up people will be able to get to the market fast. So faster, faster, faster. So getting the semiconductor to move to a more of a software-defined model
Yeah.
is really what will happen. And because everything is software-defined machines, software-defined vehicles, software-defined machines, everything will be faster and sooner. Because at the end of the day, users are using AI as a digital tool or as a physical tool, and they would like to get upgrades using software as well. So like, let's look at physical AI. So if we look at robotics as an example, everybody's talking about robotics right now.
Yeah.
It's still mostly a gimmick at this point of time. I don't expect that to be a gimmick in the long run. There'll be some useful humanoids or useful robotic or autonomous system that will be surrounding us. It's one hand it's scary, on the other hand it's going to be useful. There are definitely class of applications in the industrial and the consumer space that need that, and there'll be a lot of benefits for our daily life. But in order for a system like that to be continuously useful, you have to have off-the-air updates. All of this upgradability of cars and upgradability of robotics or physical AI machines is needed. We are moving to that model, and this is where the economics background comes into play.
Yeah.
You have new business model that come up. So our customer or customer, at the end of the day, those that provide the machine, say the robot, to the user, is saying, okay, the robot that I'm selling you right now, it costs whatever, X, but you have a subscription model that allows you to upgrade to this and that. Now, this robot will learn how to cook Thai food because other robots in the world will learn how to cook Thai food. Now, your robot will get that. So it's this kind of continuous innovation using and this is really where it gets to a complicated place. Similar hardware or same hardware. Ideal is the same hardware. So somehow you need to be able to have hardware that will be flexible enough to enable growing AI capacity. So it's both challenging, but it's also very interesting how this will happen. Or you say, hey, your robot is capable of doing Thai food, but this new cuisine that it requires more AI capability beyond blah, blah, blah. I'm just giving that as an example, but there's a new capability that the hardware system is not able of doing, and that would require upgradability. So that's really that's how it connects to the hardware design challenge of how do we create a hardware system that is bounded to the physics, meaning it cannot consume too much power and latency and not generate too much heat and go to market in the next year and doesn't cost more than X and still be flexible enough to enable the upgradability of the hardware system to a certain point. How do we predict that? How do we provide that to the designer itself to go and do it? While we as the ecosystem enabler need to provide standards that will continue to live for a longer time and provide software upgradability to the hardware.
Yeah, it's an exciting time for consumers, which of course means a challenging time for designers as those expectations continue to grow about things being improved incrementally or massively with these over-the-air upgrades or other enhancements.
Yeah, I would think that the pace that the high-performance compute investments is going is great. There are a lot of challenges in the power consumption and actually the cooling requirements. So in order for us as humanity to continuously have an AI capability on the edge, this has been talked by great leaders in the industry about having AI data centers out in space, etc. But right now, if we look at the model of electricity that is being used by data centers, I think it's last year, it's like more than the country of France is almost in the power and electricity used as in a country like Germany. So offloading that with edge-based AI will reduce the extreme need in AI on the cloud. It doesn't mean that it will not grow. Of course it will. But, for in the end of the day, in order for us to have a sustainable planet, in order for us to have a useful AI in our daily life with concerns about personalization, privacy, I think the edge AI growth will help all of the consumers in the world to have AI in their palms of their hands in an affordable way and not to put too much penalty on the planet.
Absolutely. The current rate of power consumption is obviously not sustainable, and edge has to be a major component of the solution to that problem. Hezi, I cannot thank you enough for joining us today, sharing all of your expertise and your perspectives on all of this. We really appreciate you being on the show today. Thank you.
Thank you for having me.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again for Synopsys for underwriting this episode. EE Times Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. EE Times Current is produced by EE Times and Coop Studios. Our editors were Helena Melberg and Aaron Garrison. I'm Eric Singer. Thanks for listening.